Hello, everybody. So we are still talking about the atomic structure, and we are gonna start talking about the other part of the atom, which is the electrons. So we talked a lot about the nucleus and the components of the nucleus, the protons and neutrons, and all this kind of stuff. And now we're gonna talk in more details about the electrons and how do they rotate around the nucleus. So the electrons. From the observation that we knew before, we knew that the electrons rotate around the nucleus, and or they are kind of placed around the nucleus, and because of the attraction force between the nucleus and the electrons, because of the different charges, the electrons cannot be stationary. They have to keep moving. It's like having a ball like this, and you are holding it with a rope, and you're rotating it quickly. Then there are two kind of types of forces acting on this ball, which is the centrifugal force, which wants to move it further, and the attraction force or the tension in the string that's keeping it from going the other way. So this is the same thing in the electron. You have two forces, the attraction force with the nucleus and the centrifugal force, and this is the only explanation that you can think of that makes the electron stay around the nucleus. And what we're gonna see in the next slides is gonna be very close to what you see in the universe when you like think about the sun and the planets rotating around it. It's kind of the same thing. There is attraction force because of the gravitational force between the huge planets and the sun, and at the same time they do not get attracted to the sun because of the centrifugal force that the planets are rotating around the sun. So it's kind of the same thing happens here. So the model that was put in the very beginning was assuming that the electrons rotate randomly around the nucleus. They don't have specific paths, they just rotate randomly around the nucleus, until the more experiments were done. The first experiment was done on hydrogen. They had hydrogen in a discharge tube. It's kind of the same tube that we discussed before. It's a tube where energy was put to the hydrogen atoms, and the the electrons get excited and then return back to the original energy level or the original location. So the emissions that were coming of the hydrogen when the electrons were rotating back were collected, and as you see, they were forced to move between two slits. And the beam of the electron is passed through a prism or what we call a spectrometer. It's kind of something that splits light into its or the waves into the components. And this is what we saw here. So what we saw here is that the spectrum that we found was not continuous, and we only saw red light, green or bluish green, blue violet, and violet, and we know the wavelength of all these colors. And this was very surprising because we expected that if the electrons are moving in random paths around the nucleus, the electron will emit any kind of wavelength. It's not specific wavelength. So it moved from one place to another, or from one place to a third place, or it will move randomly between locations around the nucleus, and then we will get all kind of waves coming out. But having the waves coming in a specific wavelength, which means that it moved from a specific place to a specific place. And in this case, there is no way that the electrons are moving randomly. It has specific locations. It takes a specific amount of energy to go from one place to another, and when it returns back to its original place, it emits the same amount of energy. And this is what we see here. We don't have any emissions in this region, which means that there is no place electron can stay between these two places. And this was a very good thing to know, because we knew at this time that there is what we call the energy level, We found that the electrons move from one energy level to another following this equation. And this equation, the lambda is the wavelength of the light, which is 410, 434, or 486, whatever the number that we have here. And this is a constant, and which is called Rydberg's constant. And n and m are integers, so we have here this equation. You can put any value of n, it's not any value, just integer values of n and m, and then you would find that the lambda that we will get here fits with one of these numbers that we have here. And this was a very, very good thing to know, and it changed our model about the electron rotation around the nucleus. And then Niels Bohr was a very smart guy, actually, and he was a very great scientist, and he put his atomic model based on this observation. And he stated that the electrons rotate around the nucleus in circular orbits, and only certain orbits are allowed. It's not any orbit, it's a specific orbit like this, and this. We cannot find any electrons in between this 1 or 2, or between 2 and 3. It must be here, or here, or here. And each orbit has its amount of energy, and later he called it energy level. So each energy level has its amount of energy, and to go to another energy level, it has to acquire the amount of energy that's enough to get it to go from here to here, and when it comes back, it will emit the amount of energy that or the difference of energies between these two energy levels. The amount of energy, he called it quantum, and that's why we call this the quantum mechanics or quantum theory, because it's based on the quantum, the very, very small amount of energy that is needed to move the electron from an orbit to another. And the energy is follows this equation. It's h multiplied by nu, or the frequency. It's like f here. Sometimes it's called f, and sometimes it's called nu. And this is how we can calculate the amount of energy a specific electron needs to take so that it goes to another energy level. So this is one of the first realistic models, which are very close to the actual shape of the electron rotation around the nucleus. And then he was able to get a more accurate shape of the equation that we just mentioned here. So we just put constant multiplied by 1 over n square minus 1 over m square, and he put it in a more more mathematical way. So he calculated the energy from the kinetic energy and from the potential energy. And he said that this is the attraction force, which is based on the Z, which is number of electrons, and this is the charge of one electron, and the permeability of space. Anyway, so he said that this is the energy of attraction, and I have already everything here, so you can read it by yourself. And he put the energy in this form. So this is the energy of one energy level. I'm sorry, there was a derivation to this equation, so I didn't include it here. So this is the difference between the potential and the kinetic energy, or putting them equal to each other, you'll get this shape. So this energy is going to be RCH divided by n squared. So this is for one energy level, and if you have a difference between two energy levels, it's going to be like this. So this is the number of energy level 1, 2, 3, 4, whatever. And this is the energy that is emitted when the electron goes from N2 to N1. This is how we calculate it. And then we started to get more understanding of the energy levels. We just knew that there is energy level, but we didn't know how many electrons are there in the energy level. We didn't know any more information. And this is what we are going to talk about in the next video. So I'll see you then.